we've talked about how stars like the sun die, and the end product of a mid-mass star, so anything from about half a solar mass up to somewhere around 8 solar masses, is going to be a white dwarf star. And the white dwarf star is the end stage. Not much happens after that. The outer layers blow off into space, become a planetary nebula, which dissipates in a star medium. But the white dwarf remnant, and so just stellar remnant, the white dwarf remnant doesn't really do much. It just gradually cools off and crystallizes. Now, that explanation as to what happens really is only valid in the case of a white dwarf that's all by itself. In other words, a singular star. In binary systems, then something else can happen, because what might happen is the other star might eventually die, and when it dies, that can affect the white dwarf that's already there from a previous star dying. So what would happen in a binary system? So what would happen is you have one star, the one that has more mass is going to die first and leave a white dwarf. So imagine that we have a white dwarf. So imagine you have a star, you have two stars, and they go through all the different stages of their life. One star eventually becomes a white dwarf star. Well, what about the other star? As the other star gradually expands, then remember the white dwarf has a Roche lobe. The other star has a Roche lobe. We talked about Roche lobes when we talked about binary stars. So if the other star expands and fills its Roche lobe, then stuff can start leaking into the Roche lobe of the white dwarf. And then that stuff would spiral inwards. That's kind of what the diagram down at the bottom shows. You have a red dwarf right here that is filling its Roche lobe. So its Roche lobe is like that. The Roche lobe of the white dwarf is like that. And so material is spilling over into the other Roche lobe and spiraling in an accretion disk into the white dwarf. Well, what kind of material is it? Well, what's the outer part of the star? Hydrogen. If you don't know, you guess hydrogen. So the outer part of the star is hydrogen. And so the hydrogen is spiraling into the white dwarf. And so what's happening is it's building up on top of the white dwarf. Well, the white dwarf is mostly carbon, some oxygen. Really heavy white dwarf, high mass white dwarf, is going to have some neon in it, because you're going to go through the next stage fusing carbon into neon. But so it might be a neon-rich white dwarf if it's a very high mass white dwarf. But essentially, what happens is that material from the other star is going to spiral in. It's mostly hydrogen. So that hydrogen builds up on the surface of the white dwarf. Well, the white dwarf is a degenerate electron gas, so this hydrogen squeezes in on top of it as tight as it can squeeze. The more hydrogen you put in, the more squeezing, the hotter it gets, the more energy it is, the more compact it gets, and it just sits there. Well, it just sits there to a point. So what's going to happen is that the core, which is carbon, a little bit of oxygen, is going to end up with the outer part of the star, which is some helium and some hydrogen falling onto it. And the outermost layer is going to be hydrogen. What's going to happen is eventually that hydrogen is going to be so compact and so hot and so compressed that it starts fusing. But it's a degenerate gas. So when it fuses, then rather than releasing energy to make it expand, the energy actually allows it to compact more, which makes it fuse even faster. And so it fuses furiously and creates a runaway explosion. Imagine something almost the size of the Earth as a hydrogen bomb. So that's kind of what you're talking about here, this enormous explosion. And that explosion then blows away the outer shell of the white dwarf. And the outer shell is still going to be mostly hydrogen that's fusing, and some helium and some carbon and oxygen that all that stuff's fusing into. And so all this stuff goes spewing outwards at exceedingly high velocity. Okay. So an animation here, stuff spiraling in, and then you get this giant explosion. The explosion blows away the outer shell. It also blows away the accretion disk. And so you end up with this giant explosion. The giant explosion that you see there, will eventually be visible for a long ways away. So here's a picture here of a famous nova that happened in 2001. And on the left is an image that was taken of a region of the sky. On the right was a picture taken of the same region of the sky at a different date, after that star exploded, after the white dwarf exploded. Now, the white dwarf survives. You have this massive explosion, but the white dwarf itself survives. And so what happens is, a long way away, you normally would have a star that's too dim to be seen with the naked eye, and then suddenly you have a star sometimes visible with the naked eye, or sometimes it was a star too dim to be seen in a telescope, and suddenly it's now visible in the telescope. And so this is a new star. At least it looks like a new star if you're looking at it. And so the term we have for that is a nova. And so the nova is the term applied to this brand new star. And so you can also tell, sometimes there's a variable star there, because what happens is, as the companion star is spewing stuff into the white dwarf, or leaking stuff in the white dwarf, the stream of stuff will hit the accretion disk, and it will make a hot spot. That hot spot, as it orbits around, if you're off over in another area looking at it, you'd see the hotspot occasionally go by, and so this would look like a variable star, because you'd see this thing brightening up and dimming down on a relatively regular basis. Likewise, you always, when you have an accretion activity, you have these jets of material coming out, and you looking into the jet, you'll see blobs of stuff coming out now and then, as it would get brighter and dimmer. So this would actually be a type of variable star, what we call a symbiotic star, a symbiotic variable. Though really, I think it should be called a parasitic variable, because the white dwarf is eating the outer parts of the other star. Eventually, that white dwarf, if it reaches that level at which the gases start fusing, it goes into runaway fusion, and then you get the nova. The nova is a massive, giant explosion. It blows away the parts of the outer layers of the white dwarf, blows away the accretion disk. But the white dwarf is tough. It survives. The other star is tough. It survives. But you would be able to see a very faint, expanding cloud of gas from a nova. When the Hubble telescope was launched, one of the things it looked at was a nova that occurred in 1992, and was able to see the expanding cloud of gas. Sometimes you have a white dwarf that's very compact, very high mass white dwarf, and so just a little bit of gas falling onto it reaches that threshold to start a nova. Most of the time you get a nova, and it takes thousands of years for enough gas to fall onto it to make it explode and become a nova. But for some of the white dwarfs, it doesn't take nearly that long. You can actually have enough gas to create a miniature nova every year, or even every 6 months or so. And so we call that a dwarf nova. A particular variable star, U Geminorum, was known to flare up on a regular basis, and it's been determined that U Geminorum is, in fact, one of these dwarf novae. And any star that does this sort of thing is called a U Geminorum star. And so this gives the basic ideas of how a nova works. When we were talking about the core of a star, though, we said that a degenerate electron gas, or when we talked about a white dwarf, a degenerate electron gas cannot be sustained beyond 1.4 solar masses, degenerate hydrogen, helium, and so forth. And so Indian astronomer Chandrasekhar worked out the mathematics of that, and so we call that the Chandrasekhar limit. So the question is, what would happen to a white dwarf that actually got if it was very close to 1.4 solar masses and then somehow became more than 1.4 solar masses? And what would happen to it? Because it would not be able to sustain itself as a white dwarf. It would not just simply have a nova. So that will be our next topic of study.